Okay, so here's our transformer. Actually, what are we looking at here? VA first. Apparent power ratings. Okay, so we talked about voltage ratings. We'll come back to turns ratio, which is the same as your voltage ratio. So the apparent power of a transformer primary winding, so the rating is equal to the apparent power of the secondary winding. So if you look at a transformer nameplate, it is not rated by its current. Okay, how much current can go through it. It is rated by the apparent power. So if I said I had a 500 VA transformer, that means I can, the primary of that transformer, the primary winding is rated at 500 VA. If I look at the secondary, the secondary is rated to supply 500 VA. So the secondary winding is rated at 500 VA. So let's have a little example here. If the primary winding here is rated at 120 volt and 0.5 in an amp, 120 times 0.5 is 60 VA, right there. Laser pointer, 60 VA. The secondary, if I take 12 volts and times by 5 amp, it's equal to 60 VA. So this would be what we would call a 60 VA transformer. So one thing to remember, the VA rating of a transformer is for both the primary and the secondary. So that means VAN is the same or equal to VA out. When I put a transformer under load and I'm no longer looking at the rating of a transformer, whatever the output VA must come into the transformer, so that is the input VA. So whenever we look at a load on the secondary on a transformer, we're not too concerned with the true power of it. What we're really concerned with is what is the VA of this load. So on a 60 VA transformer, the maximum we could load this transformer to would be 60. Now we don't usually load a transformer right up to 60 or its maximum VA. All right, so erase that. Or kVA. kVA in equals kVA out. So same thing. Kilovolt amps in equals kilovolt amps out. Okay, so we're going to use that to figure out the VA rating and the voltage rating, which are both on the nameplate of a transformer. It's the voltage of its primary and the voltage of its secondary, to determine how much current can go through the primary and how much current can go through the secondary. So if we call back the apparent power formula, so S, which is VA, right? That is your VA is equal to E times I. So we're just going to transpose this to figure out the current of the primary. So the I of the primary is equal to the apparent power rating of the transformer. So this is rated current that we're figuring out. Is going to be equal to 9600 VA divided by 2400 volts. So I is equal to S over E. Okay, so I, the primary, 9600 divided by 2400 amps. The primary current rating is 4 amps on this transformer. Secondary, we can do the same calculation. S of the secondary is the same as S of the primary. This is a 9.6 kVA transformer. So if I want to figure out the I of the secondary, the rated I should say, this is its rated value or maximum value, we're going to go 9600 VA divided by 240 volts. That comes to 40 amps. And there you go. Let's do a quick little, let's figure out the ratio of this transformer while we're here as well. What is the voltage ratio of this transformer? So that would be V primary to V secondary. So it's 2400 divided by 240, or sorry, 20, yep. So 240 volts to 240. So this would be a 10 to 1 transformer. So 2400 divided by 240 is 10. 240 divided by 240 is 1. It's a 10 to 1. Let's look at the current ratio now. So the current ratio would be I primary to I secondary. So the current on this is 4 amps on the primary to 40 amps on the secondary. So if we express this in lowest terms, We divide both sides by 4. So 4 divided by 4 is 1. 40 divided by 4 is 10. So it's a 1 to 10 for its current ratio. So we call this a current ratio of a transformer. Notice that the current ratio is exactly opposite the voltage ratio. The voltage is 10 to 1. That means the current has to be a 1 to 10. So we can use this if we know the voltage ratio or the ratio of a transformer. When we just say ratio, that means voltage or turn ratio. And we could use that knowing that the current ratio is opposite. So, for example, if I said that this had 3 amps going through the primary, could we use our ratio to determine the current flow through the secondary? Well, sure. 2400 to 240 makes it a 10 to 1 transformer. So the current ratio is exactly opposite, 1 to 10. So if I've got 3 amps on the primary, I times that by 10, I would have 30 amps on the secondary. I could use this opposite way. If I said I had, let's say, 20 amps. We'll just do this in red for the next example. Let's say I had a load of 20 amps off this transformer going out. So we know that we'd have to have 20 amps flowing through this winding. The current ratio is 1 to 10. So for every 10 amps on the secondary, there's only 1 amp on the primary. So 20 divided by 10 would be 2 amps. So we can use these ratios to quickly figure out what the current is in different spots. Okay, so let's use our apparent power. We've got a 2400 to 240 volt transformer here, and we have a 50 kVA transformer. Let's use that 50 kVA and determine the maximum load that can be applied to the secondary, so maximum current load, and then the maximum current that would be allowed to safely flow through this primary without overheating it. Okay, too much current. So the transformer ratio here, first question, well, that means really voltage ratio. 2400 to 240, that gives us a 10 to 1 transformer. Rated primary current. Okay, so we know that the S of the transformer, and specifically the primary, is going to be equal to the primary voltage times the primary current rated values. So if I wanted to figure out the I primary, I take the apparent power rating of the transformer and divide it by my rated primary voltage. So we're going to go 50 kVA or 50,000 VAs, or 50 times 10 to the 3 if you want to put it in your calculator that way. And we are going to divide it by a rated primary voltage, which is 2400 volts. And that comes to 20.833. All right. How about the secondary? Well, a couple ways we could do this. We could do the apparent power formula like we just did. Figure out I, the secondary, rated, would be equal to the S of the transformer divided by the voltage of the secondary. So once again, 50,000 VA divided by 240 this time. And that would come to 208.33 amps. The other way we could have done this is we already knew the primary current. We know we got a 10 to 1 transformer, so the current ratio would be opposite of that, 1 to 10. So for every 1 amp on the primary, I'm going to have 10 amps on the secondary. So using that concept, 20.88 amp, 833 amps times 10 would be equal to 208.33. Okay. So turns on the primary and turns on the secondary. So we talked about this voltage ratio. So let's go look at our input and output voltages here. Our H voltage is 120 and our X voltage is 16 volts. So we could figure out the voltage ratio is 120 volts to 16 volts. So if I want to express that in its lowest terms, 120 divided by 16 gives us 7.5, and then 16 divided by 16 is 1. So 7.5 to 1. So that would be the voltage ratio. Now, in this case, we've indicated how many turns are on this transformer on the primary and how many turns are on the secondary. So if I call this side primary just for our example, and this side secondary, it's a step-down transformer, we could figure out what the turns ratio is. So that means number of turns, so N symbolizes number of turns of the primary to number of turns on the secondary. So in this case, we've got 240 to 32 turns. So that's physical windings or turns that go around the core. Okay. So if we express that in its lowest form, I'll take my lower number here, 32. So I'll take the 240, I'll divide both sides by 32, and we should get 7.5 to 32 divided by 32 is 1. Just confirm that. 240 divided by 32 equals 7.5 to 1. So we can see the turns ratio and the voltage ratio are always exactly the same for any given transformer. Those number of turns determine that turns ratio. So we have another ratio yet. It's called volts per turn. All right. And I'm just going to erase this and we'll talk about that as well. So erase all ink. So if I know how many turns are on this primary here of 240 turns, and I know the voltage across it, so whatever we apply for a voltage across it, say that its rated voltage is 120 and we apply 120 to it, and we got 240 turns, I can figure out a volts per turn ratio of the transformer. And what's good about that is that whatever the volts per turn ratio of the transformer that is established on the primary is going to be the exact same volts per turn on the secondary. So let's talk about what I mean here. If I got 120 volts on the primary and I divide it by 240 turns, that gives me 0.5 volts for every one turn on the primary. So we have 1.5 of a volt drop per turn on the primary. Well, that voltage, that 0.5 for every one turn, is exactly what gets induced on each turn on the secondary. So it induces that voltage through the core onto the secondary. So in this case, if I know on this side that I've got 32 turns, and I know that I have 0.5 volts per turn on the primary, that it's got to be the same on the secondary, I can take 32 turns and times it by half a volt for every one turn. You see turns cancel out, so I'm left with 16 volts on the secondary. So volts per turn is the same on the primary as it is on the secondary. I could figure this same thing out if I knew the secondary turns and the secondary voltage. I could tell you the volts per turn of that transformer. And it's the same on the primary as it is on the secondary. So I'm just going to erase this.